series organized by Skill Center, Vidya Academy of Science and Technology, Trishur, in association with ISTE Students Chapter. Today we have Dr. Amit Bhaya as the speaker. Now I invite Dr. Sudha Balagopalan ma'am for the welcome speech.
Good evening, everyone here. I can see that, of course, our warmest words of welcome are due to Professor Dr. Amit Bhaya. He is a senior professor in the Federal University of Rio de Janeiro in Brazil, and he is with us today. And we are proud to listen to him on the topics that are displayed on the screen, as you can see right now. Meanwhile, let me try to welcome everyone here. We see some of the trust people here, the trust of our college. I see some directors here. Our principal has also logged in. Some of the faculty members, as also faculty members from outside colleges, because some of them grew in Vidya. Then our students, as also students from outside, and many professionals have also logged in. And they'll be logging in soon enough when they get the connection. So this is so with very so let me, on the 6th day of our international webinar on project ideas from different parts of the world, welcome you to this event and to this session essentially, where I hope you know that each of these sessions were distinct, separate, unique, but moreover converged pandemic. Coming to Professor Bhaya, what I'd like to say is that he's not a stranger to us. In fact, he was an eminent professor, eminent speaker of the first international conference of Vidya, organized by the Electrical and Electronics Engineering Department way back in 2010. I'm very happy to announce that whatever he seemed to be very accepting of the hospitality that we offered and the humble offerings that we had to offer from a remote college in a remote village, which he was very happy to accept and be very accommodating. But now I know why it is so, because I had a glance at his biodata, and I noticed that he took his honors degree from IIT Kharagpur. And then he took his PhD in just 2 years, and that too from University of California, Berkeley. So such a brilliant professor will always behave in this particular manner. Thereafter, I met him in Malta for an international conference. He remembered me. That in itself was gratifying for me. And I was alone in Malta because of the issue, because of visa issues. And we had to cancel our trip to Italy. But now on hindsight, it looks good, because the COVID-19 pandemic had not attacked with as much ferocity as it has done right now. You must all be aware that Brazil leads us. Brazil leads India right now, and US is at the top. Anyway, moving on to what happened in Malta, I was very happy to. In fact, I was amazed to see that he was connecting or associating control theory aspects to supply chain management. Okay, so this is what he is. Okay, and moreover, in fact, I was lonely there. I had another problem that I had lost all my luggage, and there weren't many Indians, and he was always with me, and in fact he also tried to help me to put up my posters. So this is Professor Amit Bhaya, and we have a small connection. Of course, he is not a Malayali, but we have a small Malayali connection. His sister is a celebrated poet, Rukmini Paya Nair. And if you look at, you can see that she has some very impressive poems already published. So that's only one aspect of it, which will not be read in the biodata, which is going to be read soon. So I just wanted to welcome, as also introduce Professor Bhaya in a very informal manner. Though I hope that though since he has lived in Brazil for so many years, his pronunciation might be a little different from ours. but I hope that in fact, he has already taken into consideration the kind of the number of the kind of students, the motley mix of students that we have, and whatever we can right now. And I'm hoping that he'll be able to respond accordingly in his address. So I give so again warmly welcoming not just Professor Baya but everyone logged in today, and also hoping to log in later on. I conclude and give back the mic to the panel for introducing Professor Bhaya in a very formal manner. Thank you everybody for logging in today to the sixth episode of International Webinar on Project Ideas from Different Parts of the World. Thank you.
Thank you, ma'am. Next, I invite Mahalakshmi A, Assistant Professor, Department of CSC, for introducing the speaker.
Good evening, all. I am very pleased for introducing our resource person, Dr. Amit Baya from Brazil. He was graduated with honors in electrical engineering from IIT Kharagpur and master's degree in electrical engineering from the University of California, Berkeley. He is a full-time professor in electrical engineering at the Graduate School of Engineering, Federal University of Rio de Janeiro in Brazil. He has worked in the area of control and systems theory and applications with emphasis in the following areas: metric stability theory, applications of switched and variable structure systems, stability of neural networks, mathematical ecology, parallel computation, and control perspectives on numerical methods. Recently, he has worked in the area of optimization and control perspectives on problems arising in business and finance areas. He was honored with a research fellowship by the Brazilian National Council for Scientific and Technological Development. And also, he has carried out several consultancy projects in the areas of control and computation. He is one of the associate editor of IEEE Transactions on Neural Networks and Learning Systems. Once again, I welcome you, sir, to the program. Now I hand over the session to Dr. Amit Baya for speaking about the topic Modeling Market Share Dynamics, Population Dynamics, and Epidemics. Thank you.
Okay. Well, good evening to everybody. Thank you very much for these introductions, which are very complete and perhaps very effusive. I don't know if it's all deserved, but anyway, let's get on to the topic of my talk, which is modeling market share dynamics, population dynamics, and epidemics. The subjects seem very distant one from the other, so I'm going to try and connect them. That's my first job. So the question is, what do these three topics have in common? And essentially, the dynamics of growth, whether it's positive or negative, is of great interest, right? So whether your market share is growing or decreasing, populations, you can have overpopulation, underpopulation, and in an extreme case, even extinction. And then disease, disease grows, in other words, spreads. That's the verb you associate more commonly with disease. And the key idea is that growth or spread in all these cases happens through contact between different populations. So taking the case of market share, for instance, given a specific product, you might have fans of the product, you might have critics, people who hate the product, and people who are neutral, right? In the case of population dynamics, if you take, let's say, the case of mathematical ecology or ecology in general, you have predators that feed on prey. So the dynamics of that happens as you know, whenever a predator encounters a prey, if it's hungry, it's going to try to eat the prey, right? And there is a probability that the prey might escape. So what happens in the encounter is critical, right? And then in the case of disease, of course, you have a susceptible population, which is pretty much everybody at the beginning of an epidemic or at the beginning of any disease taking root in the population. And so you have a susceptible population. Then some people get the disease, so they migrate to the infected population. And then if things go well, they recover and they migrate to the recovered population, which might have the characteristic of making them immune, or maybe not. Anyway, there are populations that interact with each other. So in all cases, there is the question of growth, and there is the question of how this growth is affected by the interaction between different populations, right? And so this means that there should exist similar mathematical models in all these cases. And that is indeed the case, which I'm going to try and show you during this talk. Okay, so what's modeling and why should we care about it, right? So, by the way, am I speaking too fast or should I slow down?
I hope someone says, because for me it's okay.
It's okay. Okay. I can slow down a
Any
little bit.
student?
Seems fine, sir.
Okay. My accent is comprehensible despite the fact that I've been away from India for so long. Okay. So what's modeling and why should we care about it? Well, I'm specifically going to talk about mathematical modeling, and what that refers to is writing down a set of equations that describe some phenomenon. More specifically, describe how there is growth or decay. So in other words, the evolution or the dynamics of this phenomenon, right? One reason why this is now very important to do is that data is now everywhere, right? So if you model a phenomenon and you have data on the phenomenon, then in principle you can use this data to validate your model or to come to the conclusion that your model is not valid, right? And if data is not available, then a good model can be used to predict it, right? So for instance, if you're working with chemical reactions and you want some data about something inside the chemical reactor, which is a hostile environment. Maybe you're not able to build a sensor that can withstand that hostile environment. So if you have a model, maybe you can predict that temperature or concentration of a chemical in that particular inaccessible place, right? So models are good for this kind of utilization as well. And with a model, and knowledge of which variables influence the behavior of that model, you can use these variables to modify or control the outcomes of the phenomenon that you are modeling, right? And just to make a distinction between the activity of mathematicians and the activity of most of us who are engineers, mathematicians study properties of dynamical systems. So that the dynamical system is something that is either God-given or is created in the mind of some mathematician, and then you study properties, right? Whereas control engineers typically take the model and try and seek to modify its properties. So a key engineering objective in this context is to control a given dynamical system in some way, right? And we'll see some specific examples of that. So I should say a little bit about what control is, or what my view of control is. Of course, as you know, there are different meanings in different fields. So you have a remote control, which you use to control your television in some sense. Then there's the term control freak, about people who want to control everybody and everything in their environment. There's a term control group in medicine, which refers to a group in which you control the variables of the parameters of the experiment in some sense, as opposed to some other group which is not controlled. And in biology, control refers usually to something known as homeostasis. So if you look at our body temperature, we can be out in the hot sun, with the temperature at 40 degrees, and then go into an air-conditioned room with the temperature at 18 degrees, and yet our internal body temperature remains around 37 degrees without change, which is fantastic if you think about it, because something is controlling your body not to overheat or get too cold, right? This is not true of the so-called poikilothermic reptiles like lizards, which is why they need to be in the sun to maintain their body temperature, right? So they don't have control of body temperature. In engineering, control refers to the fact that we want to make an object behave in accordance with certain commands or maintain a system at equilibrium despite disturbances. So the example I could give you to think about is, let's say, a telescope pointed at a stellar object. And this telescope is on Earth, so it's subject to the rotation of the Earth, which you could consider as a known perturbation, but also gusts of wind and vibration and so on. And despite all that, you want to maintain the telescope pointed at a stellar object, right? And the key idea in doing this is feedback. So here's an example from everyday life. This is a flush in the toilet. When you press the inlet valve, when you press the outlet valve, water, this valve goes up and water gushes out here into the toilet bowl. And this is the water level here with a float. And as you can see, as soon as the water level goes down, the float, which is floating at the top of the water level, goes with it. it pulls this lever down and brings the inlet valve to the open position, and water rushes in, so that the level of the water in the cistern goes up. With it, the float goes up and pushes the lever, the inlet valve back down, shutting off the water supply at the ideal level. So in terms of a control diagram, which control theorists are fond of making, you have a water inlet, you have an inlet valve, you have a reference level and the float, and essentially you have these loops which give you feedback loops which give you information about what's happening at some measured variable, and you control by means of doing that. So this is a key idea in control. Okay, and finally, the other theme that I wish to introduce is optimization and optimal control. So as you know, in engineering, it's often just not enough to just achieve some goal. You need to do it in some extremal fashion. In other words, as cheaply as possible, as quickly as possible, and so on. Now, in general, optimizing or minimizing or maximizing, which I refer to with one word as extremizing a function, that's the subject of something called optimization, as you know. And if you want to control and optimize at the same time, then you're led to something that, as the name suggests, would be called optimal control, right? So what I'm going to do is to weave some of these different strands together in this talk. And I'll go right into the first model that was made as far back as 1957. I know that many of you were not even born then, right? But these two gentlemen, Vidal and Wolf, at a consulting company in Massachusetts. In fact, I think both these guys were professors at MIT for some time. Anyhow, they wrote a paper in 1957, and the main questions they were concerned with are, how does one evaluate the effectiveness of an advertising campaign to sell a product? How should the advertising budget be allocated amongst different products and media? Mind you, in 1957, media meant print media, meant billboards, and so, and what criteria should determine the size of how much money you spend on advertising, right? And this was published in a journal called Operations Research. Operations Research is a term used in the management sciences to mean optimization, right? To mean all the technology associated to mathematical programming problems like linear programming, quadratic programming, and so on. Okay, so I'm not going to actually answer the question, but I'm going to give you a little bit of detail about how they did this modeling. And one interesting feature in this model that they proposed is that they actually base their model on data. So this is a paper again in 1957. You see that the graphs are this is a log graph, a log scale on the vertical axis, and a linear scale, a log linear graph on the time axis, and it's actually plotted by hand, right? And what you see is a linear decay in sales for a product that is not advertised, right? And similarly, for some other product, you see a linear decay along time in sales because you are not advertising the product. So what they hypothesized to get into their model right away is that you have a variable called S, called sales, right? And the market has a certain maximum level, M, which you call market saturation, and U is the advertising expenditure. Alpha is the effectiveness of that, so response coefficient. And so the total sales divided by the total size of the market is a fraction of the market that you have managed to conquer, to sell your product to. So 1 minus that fraction is what is not conquered by you. And notice that the advertising is acting on the fraction of the market that you have not yet been able to sell your product to, right? So that's this first term. Now forget about the first term for a minute and concentrate on the second term. And let me scribble here a little bit on the screen. So this is actually the equation. The time derivative, the rate of change of the sales. If you didn't have the first term, it would just be this, right? And as you know, the solution of this equation is exponential decay. So the solution of this looks like exponential decay. And if you take the log of this, you see the linear decay that I showed you, that they plotted in the previous slide. So this is a linear decay in a log scale, right? So this is why they have hypothesized that in the absence of advertising, so if you didn't have this term, then your sales would decay linearly on a log scale, right, or exponentially, as this equation indicates, right? So that's the basis of their model. Okay, so that's a very simple model, and an extraordinarily effective one, because it's still being used, almost 63 years later. And you can normalize this model by dividing through by the total market size. So you get a model that looks like this, where your sales divided by the total market size is the normalized market share, right? And dividing alpha, the response coefficient, by m, you get the normalized advertising response coefficient. And you can discretize this equation, because this time derivative of the normalized market share is actually, as you know from calculus, I can write this as the difference of x at time t plus 1 and time t divided by some h, and as the limit h goes to 0, you get the derivative, right? But I'll just be very not imprecise and choose h equal to 1. So then you get x of k plus 1. I move this over to the other side, and this is what the discrete time version of the Vidali-Wolf model looks like, right? So this is the market share at time k. This is the amount you add to market share by advertising and convincing people to buy your product, and this is the decay that happens because, well, so this is an interesting question. What does this actually represent? This represents, as I said, if you don't make any advertising, people tend to forget about your product and stop buying, right? So an interesting question in this context, which I'll come back to, is what happens to these people? They stop buying your product, right? But you could hypothesize that they start buying somebody else's product, right? And we'll talk about that in a little while. Okay, so I'll get back to this question of where do lost sales actually go, right? Okay, so 50 plus years later, what's the situation? Advertising has moved to digital channels, right? So people advertise on Facebook, on Instagram, on YouTube, and so on social media in general, right? And the new context is termed word of mouth, right? What's the key idea? The key idea is that you have interaction between customers. So you have positive word of mouth, which is from satisfied customers who have nice things to say about your product. You have negative word of mouth from dissatisfied customers who say, well, this product, it sucks, it's no good, and so on. And you have many examples of this: online product reviews and ratings, likes on Facebook, and so on. And look at the title of this paper, which I'm not going to go into in detail. I'm just mentioning the paper so you can see the keywords that I've highlighted. It's a paper about advertising, and it refers to word of mouth, and it has the word contagion in a sales model, right? So it's bringing together all the ideas that I mentioned in the title of my talk, right? Marketing, so advertising for marketing, for sales. Something to do with what is word of mouth, essentially. We're going to talk about that in the next slide. Word of mouth refers to an interaction between a satisfied customer, for example, and a dissatisfied customer. So you meet your friend and you say, I'm very happy with I don't know, my iPod, or my iPhone. And he says, well, I have an Android phone and I'm very happy with it, and I hate iPhones because they're, proprietary or something like that. And then you try and convince your friend that this is actually, that there are good reasons to like an iPhone, whatever. So in this interaction, some change occurs in the profile of consumption by the population, right? And so I'll talk very briefly about population dynamics models. Lotka in 1925, who was an American biologist, and Volterra, who was an Italian mathematician, they independently proposed the Lotka-Volterra model. It now bears their names. Lotka was a chemist and a mathematical biologist, and he proposed this for chemical species in reactions. So if you have two molecules of different chemical compounds, when they meet, in other words, when you add a chemical compound to another, then some reaction occurs, right? And you get different populations of chemical products as a result of the reaction. And sharks and sardines are predators and prey, and this is a very very well-known model, the Lotka-Volterra model, which says essentially, once again, let me assume that this term is not there. So the prey, the sardine, will grow exponentially if alpha is a positive number. This coefficient here is greater than 1. So if you start with one sardine, then at time k, then at time k plus 1, you'll have 1 plus alpha sardines. At time 2, you'll have 1 plus alpha squared sardines and 1 plus alpha n sardines at time n, which means that you'll get an geometric or exponential growth of sardines, right? But that unfortunately does not happen in real life. What happens is that some sharks show up, and the sharks have the following dynamic. Whenever an encounter, so this term x times y represents, roughly speaking, an encounter between the X population, sardine population, and the Y population, the shark population. So the number of encounters is proportional to X times Y. That's the idea. And you have a predation coefficient. So for every encounter between sharks and sardines, some proportion results in a shark actually eating a sardine, and that's the reason for this negative term. So you have exponential growth, but it's tempered by the fact that the sharks are eating the sardines, so this negative term here. And what they eat goes to their benefit, right? So now look at this equation. Here you have 1 minus beta, which means that if beta is a positive number, in the absence of this term, you would get, if you started at time 1 with one shark, then at time k plus 1, which is at time 2, you would have 0.9. If beta is 0.1, you'd have 0.9 sharks, then 0.99, 0.9 squared, 0.81 sharks, and so on, right? So you would get geometric decay if the sharks were unable to eat, right? But they can eat sardines. That's what we're assuming. So you get this input from the fact that the sharks eat sardines, and you get this kind of dynamics, right? So you have predator-prey dynamics, where alpha is the prey growth rate, beta is the predator death rate, and delta is the predation rate, and these are all non-negative constants. I should say, of course, that this is an extremely simple model, so there are many limitations that it presents, and I'll show you by way of mentioning that there are, as you know, there's simulation software that does wonders nowadays. So here is a screenshot showing you what this particular software called Berkeley Madonna does. Essentially, it allows you to write equations that look very much like the equations we wrote down on the previous page. So next means sardine population at time k plus 1, this word next, right? And it says that depends on the sardine population at the current time minus the predation term, and the same for the shark. And a similar equation for the sharks. You give the initial populations, you give the values of alpha and delta, give the time at which you start, the time at which you stop, and you hit the button run, and you can see these graphs, which are time plots, and you see the oscillations. So when the shark population is low, not much predation is going on, and the sardine population is rising. And then as the shark population begins to rise because they're eating these increasing numbers of sardines, the sardine population eventually, having reached a peak, begins to go down. When the sharks get too greedy and they're eating too much, the sardine population, the prey population declines to its low value, and this goes on in cycles, right? So these are oscillations that you see typically in biological systems. A nice feature of this simulator is that it allows you to put sliders like potentiometers on all the parameters that you have in your model. In other words, these parameters. And as you move these buttons and slide them, you change the value of the parameter, and these graphs change in real time, right? So I won't spend too much more time on this, but we can come back to this if there are questions. So anyway, one other thing I'd like to say, one last thing is that, yes, it's easy to do this, as you can see, and it's easy to experiment nowadays. So this is a benefit of having a model, as I referred to in the beginning. Even if you can't actually measure populations very accurately, you can measure some features of the population and see whether, as your model predicts, you have these kind of oscillations. In fact, historically, Volterra was asked by his father-in-law why shark and sardine populations were oscillating so much in the Adriatic Sea near Italy, and this is the explanation he came up with. So this is, this, I'm talking to you about the historical origins of mathematical ecology, but also in some sense the origins of modeling. Are there any questions? I heard some. Okay.
Can you wait? Can you wait for the questions later on? Is it okay?
Yeah, I can wait. Yeah, sure, I can wait. I heard some.
Yeah.
Okay.
I don't think so. Yeah.
So I'm assuming everyone is with me so far, and we'll go to the next slide. So now I'll go back to the marketing case, and I'll concentrate on this because there's a lot of stuff written on this slide. Let's say you have a brand, and I'm interested in I'm the owner of this brand. I'm interested in the brand population, right? And now there are people who don't like my brand. I'll call them defectors. I know that sounds like an ugly word, but this is just a technical term, right? And then there is a population that is undecided. So B for brand, D for defector, and I for undecided. Because U is a letter reserved in control for the control action, right? So that's why I choose the letter E for I for undecided, okay? Now, what happens as a result of advertising is that you can think of advertising by the brand as predation on the people who are undecided. So the object of advertising is to make, so here's the term, U is the advertising effort, some proportion of undecided people actually buy the brand. They get swayed by your advertising and decide to buy the brand. So some people leave the undecided population and become brand consumers, right? Similarly, the defectors could also, before I talk about defectors, and of course people may get disillusioned by the brand and leave, so that's this arrow, with a negative sign because they're leaving the brand and a positive sign because they're becoming defectors. Now notice that this term is an encounter term. Every time a brand consumer encounters a dissatisfied defector, some proportion leads to the brand consumer defecting, right? Now this model is making the assumption that it is never the case that a defector or somebody who's dissatisfied goes right back to buying the brand, right? So what we hypothesize is that the defector goes through two stages. Because of the advertising bombardment by the brand, eventually the defector has second thoughts. So he or she goes into the undecided population. They're now having second thoughts, and then they might go through this channel to become consumers because of the advertising, or because they have an interaction, because brand consumers are interacting with undecided people in the undecided population, right? And that is this term here. Interaction between brand and undecided leads to a favorable decision, and you get this transition, right? So that's what these equations are actually referring to. We don't need to go into all the details, but you can see this is how much I have. I'll just do it for the first equation. This is how much I have of the brand market share. My advertising adds to that by some coefficient, and then I am able to convince some undecided people to buy my brand, and some people inevitably defect, right? The people who defect go into the defector population, so the term is minus here and plus here. The people who are leaving the undecided population to become brand customers are negative here and positive here. So you can see the color scheme with the terms. And the same for defectors who manage to convince undecided people never to buy the brand. So that's this green arrow here with the negative, positive and negative signs, right? So these are the equations that we proposed in about 2 years ago as a more modern alternative to the Vidali-Wolf classical model from 63 years ago, because basically it takes into account these word-of-mouth interactions, which could be, in fact, interactions occurring on social media, occurring virtually. You don't actually need to bump into your friend to convince him or her to buy a different product. You could do it by comments on social media, by TikTok, God knows. Okay, and the interesting thing is that we published this in the IEEE transactions. Notice the title of the journal, Computational Social System. So this is becoming a reasonably active area of research, how you make these models and how you use them to study trends in let's say in this case marketing, but you could do this to study trends in fake news, trends in all kinds of things, where the essential point is that you have interaction between different types of populations. So populations who are in favor of a brand, in favor of a certain politician, a population that is um, radically against the brand, against a certain politician, and so on. You get the idea, right? So these kind of models are now of great interest in many contemporary situations. And as I pointed out, they came from historically from models that were of great interest in the past for different reasons, right? In a sense, you could say there's never anything new under the sun. We just reinvent, right? Okay, so this three population model, it has rather rich dynamics. And again, I won't go into great detail here, but you can show things like if I make a plot on in 2 dimensions, brand versus defector, then you can show that left to or under a low level of constant advertising effort, if the brand starts with a low defector population, even under a low level of advertising, you tend to increase the brand market share and you converge to this point where the brand has the full market, right? But if you start with a relatively high initial defector population, then under advertising, you tend to go to this stable equilibrium where you have about, let's say, 30% of the market, and the people who are not buying your brand are about 70% of the market, right? Now, can you change that? And this is what this graph is showing. You can adopt a policy, and this is, as I said, a result of having a mathematical model on which you can experiment before you actually do the advertising. So what this model is telling you here in this case is that if I adopt a policy where I switch between low or no advertising and an intense level of advertising, it doesn't really matter what these numbers are. It just means that whenever I'm below my target, this XB is my desired market share. So I want 70% of the market. So as long as I'm below 70%, I use an intense advertising effort. And once I get above 70%, which is right around here, I slow down, or I either remove my advertising effort and I can coast to this stable equilibrium at about 70% of the market share. Okay. So those are the kind of things you can do using this kind of modeling, and you can do a little bit more. And so this is just to very briefly tie in with what I mentioned about optimal control and optimization. You can say that let's call the desired target market share X sub B star. Okay, so XB star, I'll just say XB star. And I introduce something which I call a performance index, J, capital J, of my advertising effort, which is U of K, right? So alpha times U of K plus beta times the error or the difference between where I am at time K plus 1, so how much of the market share I have at time K plus 1, minus what I actually desire to have, right? So this is how much the gap between what I want and what I have. And I raise that to I square that because I could be above or below, and in either case I want to get exactly to this term, right? You could say this is not very realistic because usually I would want to get to my market share, and if I get above it, that's fine too. But let's just assume for the time being that I want to get exactly to XB star. So now what's the role of alpha and beta? If I'm very interested in getting exactly to this market share, I choose beta to be large and alpha to be small. So let's say 1 in alpha and 10 for beta, right? That means that when I'm trying to minimize this performance index, I will try and get XB to be as close as possible to XB star, right? Because the weight here is large. So these are weighting terms, alpha and beta. If I have an advertising budget and I'm very interested in spending as little as possible, then I'll choose alpha large, and I'm less interested in getting as close as possible to XB star, then I'll choose alpha equal to 10, beta equal to 1, right? So this is a way of trading off your expenditure with how much of the market share you desire to get as target, right? And the idea is to choose your control, U of K, control here being the advertising effort, to minimize this performance index at each step. So this you could refer to as a greedy or one step ahead approach, because I'm at time K and I'm looking at what happens at time K plus 1. Recall that this is exactly what the dynamics tells you, right? If you apply advertising effort at time K, it gives you what you would get as market share at time K plus 1, right? This is a difference equation rather than a differential equation. But the similar things happen for differential equation. Anyway, so formally I could write this as a mathematical programming problem, which is minimize this performance index subject to the dynamics, so subject to those three equations, of which I have written just the first one here. I also want the market shares to be non-negative numbers. You don't have a negative market share normally. And the advertising effort is also usually negative, because I would be crazy to do negative advertising for my own brand, right? So these are all non-negative variables. And I might have a maximum expenditure constraint on my advertising effort. So this looks just like a typical, I'll give it its exact name here. This in this case, with this particular choice, this is just a quadratic, oops, some glitch here with the pen. Okay, anyway, QP, I can do that. Quadratic program, right? This is a mathematical description of an optimization problem that you would solve. And notice that it gives you exactly how much advertising effort you should make at each time K. Okay. So again, a benefit of having a model that you can use to decide how much advertising you should do at any given time. Okay. And once again, you can, how am I doing for time? Okay. So I'll just skip this. Essentially, these two graphs show that if you use optimal control, you get a little bit quicker to the desired market share here than you would if you used this naive control of switching, putting total advertising effort as long as you're below 0.7 and then switching off when you're above 0.7. So in other words, one-step optimal control is a good policy. Okay. That I want to connect up with all these ideas that we've been talking about are the so-called SIR epidemic models. Again, notice that these models were done around the same time as Lotka and Volterra, 1927, by Kermack and McKendrick. This is a famous paper. And what it postulates is that, as I already said in the beginning of the talk, you have a susceptible population, an infected population, and a recovered or removed population. The general term used in some of the older books is removed, because you are removed from the infected population because you've become immune, or because you die, or because you've been isolated, right? In any case, you have three populations and you transition from susceptible, to infected, from infected to recovered. And these could be thought of as compartments. So you move from one compartment to the other, or one population to the other. A common assumption is that we have a closed population of constant size. So at any time, the sum of the three populations is a constant. This symbol just means for all time. And you can write down simple differential equations that model the movement between classes. So the rate of change of the susceptible population, why does the susceptible population change? It reduces because people become infected. So you have the negative sign, the derivative is negative. Here is the interaction coefficient between infected and susceptible. So that's that we have seen this before in the marketing model, right? And also in the population biology model. And this fraction, or this amount, goes over to the other compartment. So it's negative beta IS here, and it's positive beta IS in the infected population's rate of change. And the infected population rate of change, once again, if you didn't have this term, people would get infected, and then after a while, there's nobody else to get infected. So you get a natural decay. in the infected population. And finally, here is the recovered population. So whoever is no longer infected or becomes immune belongs to the third compartment. So this is a very natural series of equations that you would write down, and they're also known as compartmental models, right? Now you can normalize, as we did in the market share case. You can divide by the total population size. So this is the susceptible divided by the total. So these are fractions between, they're all non-negative fractions, and their sum is 1, right? That's just this equation divided by n, right? So the normalized equations look like this. The rate of change of the susceptible population is negative R0 UV. The rate of change of the infected population is R0 U minus 1. And the rate of change of the recovered population is just V. Okay, that's this term going over here. Okay. So R0 is the famous basic reproductive ratio. It's the rate of infection divided by the recovery rate, and multiplied in the numerator, or the scaling factor, is the population size, right? Now this is interesting because if you look at this equation, recall that I said that these numbers are all non-negative, and since they sum to 1, that means that U something is strange with this pen. Anyway, all these numbers are between 0 and 1, right? Because they're all non-negative and they sum to 1, right? This is a U. Okay. So that means that this number R0 U is less than R0, right? And if R0 itself is less than 1, then this term here is negative, which means that the infected population is reducing in size. Okay. And also notice that if V is 0, right? In other words, that there is no infected population, then this derivative becomes 0, right? As well as this one, right? So there is no growth either in the recovered population or in the susceptible population, right? If the infected population is 0. So this particular state, U equal to 1, V equal to 0, is known as what we want to have, the disease-free state, right? Disease is, nobody is infected. Of course, everybody is susceptible, but nobody is actually infected, right? Okay. So essentially what I want you to remember from this slide is the basic reproductive ratio and the disease-free state, right? And of course, you have these simple compartmental equations. Okay, so the main result about stability of the disease-free equilibrium, I won't go into great detail here, but essentially, as I showed you, as I talked you through on the previous slide, if the basic reproduction rate is less than 1, the disease dies out. And if it is greater than 1, R naught is greater than 1, then an epidemic may occur, right? Which was the lesson we got by looking at these simple equations. Recall that if R0 is less than 1, U being between 0 and 1, this number is less than 1. So you have a negative derivative for the infected population. Right? So it will eventually, because of the negative derivative, it will eventually decrease to 0. This is very informal. You could formalize this, and that's what goes on in these references that are cited, from which I've taken some of these figures. Okay. All right. So you could actually make more complicated models of these, and I'm just going to talk about one of them and then briefly show you slides of the others. So here is a model which talks about the famous lockdown and social distancing. So what is that in mathematical terms? What it is that by removing people from the streets and locking them down in their houses, you are essentially reducing the frequency of contact between the affected, between the susceptible and the infected, in other words, this term. And what do I mean by reducing the contact? If you reduce contact, in other words, the frequency of at which a member of the infected population meets a member of the susceptible population, you're essentially reducing the infection rate. So I can write that as 1 minus U of t, where U is some number between 0 and 1, which is how efficient your lockdown is, right? That number between 0 and 1 multiplies beta, and I could call this this whole product as the effective infection rate, right? So by making lockdown or non-pharmaceutical intervention, which is the current jargon, right, essentially telling people to stay at home, that is equivalent. So the more effective you make lockdown, the higher you are making this number U, and it's equivalent to making the effective contagion rate, or I'm sorry, the effective infection rate lower, beta, right? So this is the same model that we saw before, except that beta has now been replaced by this effective beta. Right? So that's what all these uh, lockdown attempts are doing, right? It's the same model as before, but we now have the so-called lost my okay, here we so have the so-called effective beta, right? Now you can make more complicated models, and there are several such, which I'm just going to briefly mention. You have susceptible, exposed, infected, hospitalized, and dead, which is the final state. Okay, no feedback and no output from the dead state. Now here is something that you might ask: what does this arrow represent? This represents something that we unfortunately still don't have for COVID-19, which is vaccination, right? So vaccination will allow you to transition from a suspect. The most complex model that I found looking through the literature in the last few days is something by a model made by these Italian people, and I think they have some Indian connection or a sense of humor, but they called it the Siddharth model, where it has nothing to do with Siddhartha, but susceptible, infected, diagnosed, healed, ailing, recognized, threatened, and extinct. I think they also use their knowledge of English to choose these words so that they could get this nice acronym. Okay. Anyway, this is a very detailed model. It has, as you can see, 8 compartments, which I just mentioned, and different rates of transition between these compartments, right? Now, what I wanted to point out again in this propaganda talk that I'm doing for engineering, that the authors are from industrial engineering, electronics, information and bioengineering, information science, and physics, right? And only 2 of the authors are actually professionals in infectious diseases and diagnostic and clinical sciences, right? So the message is, of course, that we need to do interdisciplinary work, and also that engineers are important, right? I guess I'm talking to a crowd that's already convinced about that, but it's always a good message to reinforce. Okay, so what are some project ideas? Well, talking specifically about the state that you are all so fortunate to live in, you could model the specific control measures against COVID-19 taken in Kerala, which is, as I understand, the national champion now, using one of these models and comparing them with some other state, for instance, Maharashtra, which I believe has the highest infection rate right now. And then you could play with your model parameters to see how well your model fits the data. These data are now widely available. You can, if you log into almost any Indian newspaper site, there is a COVID, whatever it is, a COVID indicator or something, and it's hard to escape from the data. So what I'm saying is that data is available, and you can use this. Oh yes, there is one thing I did want to say about the previous slide, that these people claim that, and in fact, I think given the number of citations of the paper, this claim is actually true, that this kind of modeling actually has policy implications, right? So, which were apparently taken into account by the Italian government, right? So it's not just a mathematical modeling exercise for the academics. It actually leads to some kind of policy implications, right? Of course, if you're doing a project at the university undergraduate level, you could just gain some experience in doing modeling, and then that's the first suggestion. The second one, of course, I'm going out on a limb here. I know nothing. I know very little, only what I have seen on the internet. But and I'm sure that many of you in the audience know much more about this than me. But I consulted this page, Kudumbashri, the famous Kudumbashri organization in Kerala. And on page 512, they state that they're talking about micro enterprise development, and they state that 75% of their products are sold directly to customers, 10% to retail dealers, a little less than 10% to government departments and agencies, and the remainder to retailers and wholesale dealers. So my question in this context would be, I don't know, I must be the first to declare my complete ignorance of what they actually do, but I think that it might be a good idea to model and ask the question, is this actually an optimal mix for sustainability, given that the prices that they are selling to their own customers, to retail dealers, and to government departments and so on are not the same, right? There is a price structure. So you could ask the question, is this the best price structure? So they sell more to customers and less to retail dealers, or more to retail dealers, or how do they modify these fractions or these percentages over time so that they can maintain the whole operation running well, right? So the suggestion would be to construct a simulator. I just gave one example, and as you know, the Kudumbashree page is very rich in data. They publish all their data. It's extremely transparent. So you could construct a simulator, which in the limit could even be an Excel spreadsheet that gives you an idea. And as you know, in fact, Excel spreadsheets also allow you to do linear programming, for instance, all kinds of sophisticated things. Okay, so that's the second suggestion. And finally, take a situation which you are familiar with and in which decision making would be greatly helped by the existence of a model. Build the model and simulate it, and remember that your own ideas are always the best, right? You could take some help and some advice from old people like me, but given your age and your enthusiasm, I think there's no doubt that your own ideas are always the best, and because you also have the most passion in taking them forward, right? So here are some references. These are books which, if people are interested in reading more about these topics that I mentioned, and here are two sites which I highly recommend. In fact, if we have a little time, we could play with them. Maybe not, because I see that I'm getting to the 1 hour mark, so I should stop. And this is the site for the Berkeley Madonna, of which I showed you a screenshot during the talk. And in my own work, I have been using Julia and JUMP, which is Julia Mathematical Programming. It's a wrapper for mathematical programming code, like quadratic and linear programming. And Julia is open source. It's built by a consortium, which I think the main branch of which is at MIT, but there are other big universities in the consortium. And it is basically a MATLAB-like software, except that it compiles to native code on whichever machine you're using. And so it is much, much faster than MATLAB for most jobs. It is, of course, open source and free. And as I just said, it's high performance, so it is very popular for machine learning right now. And I must say that although it is a relatively new language, it's been in existence for about 4 years, I have been migrating almost all my code to Julia, and I'm very satisfied with it. As a disclaimer, I should say I have nothing to do with Julia. I'm not making a commercial plug for them or advertising, even though I work with advertising, as you just saw. But I am now going to make a small plug, if you permit me. And so a lot of these topics that I talked about in the business area are going to be in a forthcoming book with my co-author and a long-time co-author, Eugenius Kashkurevich. And the book is entitled Business Dynamic Models, Optimization-Based, One Step Ahead Optimal Control. Okay, so, oops, went in the wrong direction. Okay, so that's it. Thanks for listening. I can be reached here at this address, but be prepared for somewhat slow replies, because lockdown doesn't mean that I'm actually not doing anything. And finally, I'd like to acknowledge my friends and co-authors, Eugenius Kashkurevich, Fernando Passos, Federico Jandri, and also Brazilian federal and state government funding agencies. This is the National Council for Scientific Research and Development. This is the Education Ministry's branch for financing fellowships and projects, and this is the state government equivalent in the state of Rio de Janeiro. Okay, so thank you very much for your attention, and I'll be happy to take questions now, if there are any.
Thank you, sir. I think there will be a few questions. In fact, people have people have started asking you for the slides first and foremost. So that's one thing. Second is, of course, I think this applies to many aspects, whatever you presented, and some
Right.
of the projects that we are doing right now include the people who start off with the MOOC courses and thereafter they leave the MOOC courses. So there is a
Right.
people who are undecided. There's also some defectors. So perhaps quite a large number of things can be associated with whatever you are presenting. I'm hoping that just will ask you something or the other. Okay, I'll wait.
Okay. I see a lot of people saying thank you, and I have to say that I'm thanking all of you for having listened to all this for so long. Okay.
They're saying thanks before they leave because
Oh, I see. Yes, it's dinner time, right? It's time for mean curry. It's time for mean curry, right?
no, Minpari can wait, but the internet does not wait. Come on, somebody ask something directly. Switch on your mic and ask.
I hope there was not too much detail. I tried to skip some of the detail because I thought that might be too much. But
You did skip a lot of details, but then the slides were talking.
Right. Right.
So it's easy for people like us to understand, but I don't know because we have all disciplines here.
Right.
If anyone wants something to be re-explained, that's also possible. Perhaps is it possible, Professor Baya?
Sure. Okay, for some reason I should explain, and that's not necessarily a bad thing if the model is a relatively faithful representation of what goes on in real life, right? Because it can give you ideas as to what policy decisions you should make and so on, right? So my general answer would be, yes, you should make models if you can, and yes, you should confront them with data, because nowadays it's very hard to make the excuse that data is not available, right? I saw some questions that flashed by while I was talking, and let me see whether I can get back to them. Just a second. Okay, there's a question about how important it is to include allele frequency in population dynamics to bring up equations like Hardy-Weinberg. Yes. Oops. Can you still hear me?
Very much audible.
Okay.
Very clear.
Okay. Wait a minute. For some reason, okay, I got the question. How important is including allele frequency in population dynamics to bring up equations like Hardy-Weinberg? Okay, yeah, I didn't talk about specific things like the Hardy-Weinberg law, but of course, if you want to derive the Hardy-Weinberg law, you do need to take into account allele frequency. But that's a slightly different area of population dynamics. That's more population genetics, right? I talked about macro models, not micro models. But for micro models like allele frequency in population genetics, yes, of course, you need to take them into account. Is there any particular reason? There's another question. Is there any particular reason for switching from Julia from MATLAB rather to Python or R? Okay, well, maybe not right now. I could give you, because Python has a huge ecosystem, a lot of software available. But Julia actually has wrappers for both Python and R, so you can use Python and R within Julia. My reason is that Julia is high level, right? So and I was pretty conversant with MATLAB before I switched to Julia, so that's my reason. And another important reason is that the integration with the optimization software is very good. And furthermore, Julia is set up to be a high performance language. So if you are in a parallel environment, it is easy to use the parallel resources. If you're in a multi-thread environment, you can do that as well very easily in Julia. Okay, so that's another good reason for switching. Okay. Uh, there's a question about how the model is applicable for a country like India. Well, nothing that I said in my talk is actually country specific. So it's not only applicable to India, it could be applicable to Bulgaria, to Kazakhstan, any country, because populations interact and disease spreads by interaction, for instance. Okay. Or people gossip and change their opinions through gossip. So interactions occur, gossip occurs, and that's universal. It's not country specific.
I think quite a lot of applications is there for the transition models that you were talking about, because in fact, even I felt that the population dynamics has something to do with the environment also, isn't it? The purity of the environment. So perhaps...
Sure. Yes, in fact, these kind of models, I myself studied them in the context of how you control grazing on farmland. And you have to do it in a very specific way, especially if you want to avoid desertification and, especially in semi-arid environments. There are specific models for that. And you need to control the grazing very carefully so that the land doesn't get depleted, either for agricultural purposes or for breeding cattle.
Okay, are there any more questions? What about waste management? Do you think waste management can be connected to, can be modeled and the...
yeah, well...
Yeah, you have also the SIR, yeah.
Well, I don't know whether specifically one should, there's apparently a Polish saying, which is, give a man a hammer and everything looks like a nail, right? So what I mean by that is that because I talked about the SIR model, that doesn't necessarily mean that we should try to fit everything into specifically an SIR model. I think the more general message is that models in general are useful. And so for waste management, I'm sure that there are models where there exist models. And I think in those cases, maybe you have to look at the energy expenditure, right? So how much does it take to actually convert or recycle waste, and is it energy efficient, and what are the environmental benefits? But you have to look at the variables, and yes, you can make a model. It may not be an SIR model. In fact, I'm guessing it would not. But economic models that look at both the actual phenomenon and its dynamics together with some economic factors like price and energy expenditure and so on, those I think are models that are very useful for society. And unfortunately, in my view, most government decision makers don't appear either to have these models or, even worse, appreciate these models given that they exist, So I think our major role as educators in engineering is to make people aware that in all situations, it's important to have a mental picture of whatever you're dealing with, and that mental picture, convention has it that we call it a model, right? So this mental picture is a model which you feed with data, and it gives you predictions, it gives you ideas as to what policies might be good or might save you money and things like that, right?
Looks like you have answered all questions satisfactorily, and perhaps
okay.
Take one question more. Yeah, but Professor is asking a question.
Okay.
So can you share your intuition on the Kudumbasri project? What are the which model could be most suitable for it, and what is your idea on that particular project? And because here we have NSS, the National Service Scheme,
right.
It's highly associated with the Kudumbasri. There are various projects, and we have the data center. They have collected data on. So
Right.
there is a possibility for a collaboration over this project. Can you please elaborate?
Yes. Well, first of all, let me state that I have very little knowledge of what they're actually doing. I looked at the web page. I looked at some policy statements and some studies, but very little. I don't know actually very little about what is going on. However, it seems to me that there's a lot of data, as you said. There's a data center. There's a lot of data collected. And the site looks very good and very sophisticated. So I'm pretty sure that there are lots of people, intelligent people, already doing this modeling. But there's always a possibility of improving them, interacting with them, making new suggestions. For instance, I saw that there was, I think, some. Let me try and just a second. There is a project which is called. I'm logging into the site right now, and just to recall the name so I don't say something wrong. So they have several projects to dealing with food items, right? I think bananas and what is it now? Horticorp outlets, bazaars, and so on. Now, my gender. Sorry.
They have food outlets too right now.
For food outlets too. So in all these areas, there is a supply chain. There are people who actually produce. There are people who transport. There are people who stock the stores, and then there are people who sell, right? Or give. I'm not sure. And the website refers to sellers and buyers and so on. So it looks like they are selling, right? So one of the things that is always useful to do is to model this supply chain and see whether there are bottlenecks, whether it's working well, how it can be made more efficient so you minimize food wastage. If you supply too much to a place that is not able to sell it, then you have wastage, right? Or there are shortages, which is also bad, right? So I don't know whether all those models are actually already in existence. And if they are, wonderful. If not, that's an excellent opportunity to interact, right? And to make these models.
Yes, sir. Actually, now, as Dean mentioned, the Kudumba develop a model for food chain that can be transferred to waste management also. So practical help from you.
Yes, I would be very happy to do that. Yes, in fact, I think the societal impact of these projects is huge, and anything that academics can do to further this. And I'm not saying this in a political sense. I'm saying this in a sociological, societal sense. I think is extremely important because, after all, we are educating people not just to be engineers but also to be citizens of whichever countries they live in.
Thank you, sir.
Yeah.
Professor Bhaya was telling us that he'll be helping us. He even shared his email ID. I can read it. So that's how he has responded to this session. And I think the main takeaway is that the scope for modeling almost every kind of dynamism that occurs, and even with respect to desire for learning engineering and admissions in engineering colleges, etc., where whether advertisement is going to give rise